All right, I think we're good. I hope so. Um, all right, good morning, everyone. So our presentation today is going to be on basically on radioactivity and what we learned about the atom and the nucleus in particular, using this phenomenon of radioactivity. The two big ideas are here in this first slide. The idea of the half-life of a radioactive element as it disintegrates, and it disintegrates into yet another element, which was just amazing discovery, something that chemists had not anticipated at all, how that could be, how an element could just spontaneously transmute into another element. And the other is here this depiction of the very, very famous gold leaf experiment of Rutherford, leading to the discovery of the nucleus. So we'll be discussing these two things, among others, in detail. First thing to tackle is the idea of radioactivity and these uranic rays of Becquerel, and understanding just what these rays are. Turns out that there are three different types of emanations that are coming off of a radioactive element, and we'll see how these got sorted out. The figure here, the key figure here of our whole presentation this morning is going to be Ernest Rutherford. A brilliant student in New Zealand, wins a scholarship, finishing his undergraduate work, and makes it very easy for him to decide where he wants to go. He wants to go to Cambridge to work with the famous J.J. Thomson. And the scholarship then pays his way to get up to Cambridge, and he joins J.J. Thomson just about the time when Thomson is discovering the electron. He becomes fascinated with radioactivity, and that's what he wants to pursue himself as a research topic. And the first thing that he shows is, in fact, that there are at least two different kinds of uranic rays coming out of a radioactive element. He names them alpha and beta rays. He sees that they have different penetrating power. That the beta rays can go through objects, like, for example, thin paper, where the alpha rays will be stopped. And yet the beta rays will be stopped by other kinds of materials. And he makes a thorough study of this. He does very interesting what he uses. Remember the electroscope, where if you bring a radioactive element near an electrified electroscope, the leaves will collapse. We know now what's going on is the radioactive, the alpha and beta particles, or whatever else is coming off, is actually creating ions in the air around the electroscope, which then are attracted to the electrified electroscope by unlike charges attract, and that will then neutralize the electroscope. He used that means by having different barriers between the radioactive element and the electroscope. And he found what kind of barriers would allow the electroscope to be neutralized, and what kind of barriers would not allow the electroscope to be neutralized. And this is how he could tell how far these rays could penetrate through different objects. Very, very simple experiment, very simple in concept. This is classic Rutherford. This is one of the great things about Rutherford, the simplicity of his experiments, of their design, the simplicity of the materials that he uses to come to his incredible results. We'll see this a couple of times as we go through this presentation. Turns out that he gets an appointment after he finishes his doctoral work with J.J. Thomson. He gets an appointment to McGill University over in Canada, which he takes and is there for a number of years and does some of his most important early work there at McGill. He's able to show, through the same way with Thomson, about deflecting the beta particles with electrical fields and magnetic fields. He's able to show that his beta rays, which he can isolate by knowing what can get through certain materials and what can't, he can show that these beta rays are in fact a negative particle. Okay? They look very much like the electrons of J.J. Thomson. He's not able to deflect the alpha rays. Um, no matter how strong a magnetic field that he uses, he doesn't therefore know what is these alpha rays. Maybe they're not particles at all. Maybe they're a wave of some kind because they're not reacting to the magnetic field. Turns out that our friend Becquerel, the last great contribution he makes to his discovery of radioactivity, he uses the Thomson model, the Thomson experiment, to calculate the charge to mass ratio of the beta particles. And he finds them to be the same as electrons. He finds that the ratio is exactly what Thomson found for the electron. Can't be a coincidence. Beta rays are in fact beta particles. Beta particles are in fact electrons. Still though, to this day, when you read in popular science, so scientists today will still talk about beta particles. You have to know that beta particles are electrons. They will talk about beta emissions. They will talk about beta decay. They will still use the words alpha and beta because it's just part of the lexicon. It's there. It's being used. You just have to know that when people are talking about beta rays or beta decay or beta particles, they're talking about good old-fashioned simple electrons. However, these electrons are coming from the activity of radioactivity, not, you know, what we think of as electrons in some ways circling around the nucleus. This is an electron coming from the process of radioactivity. This will have to be figured out. Just what is the other? These are different electrons, and what you know? What's the story about these electrons compared to the electrons that J.J. Thomson found in the metal of the various cathodes that he was using in his cathode ray tube. So we now have understood what beta particles are. They are electrons. And finally, Paul Villard, using more powerful magnets and electrical fields, discovers the third emanation coming from radioactivity itself, the last ray, a very powerful ray, more powerful than alpha or beta particles. And Rutherford suggests that they be called gamma rays, alpha, beta, gamma. And so they're identified as a more powerful ray, but not knowing what its nature was. So we still don't know exactly what alpha rays are, nor what gamma rays are at this point at 1900. But we do have the penetrating power experiments, and we understand that gamma rays are in fact much, much more powerful than alpha or beta rays, way beyond the penetrating power of either one. This seems to be a different kind of phenomena, right? Because of its such as greater penetrating power. Because it'll be learned that gamma rays are in fact very, very high energy, very, very high frequency electromagnetic waves, even beyond the X-ray range. In 1902, in Manchester, Rutherford finally straightens the whole thing out using more powerful electrical fields. He reconstructs the experiments of J.J. Thomson, confirming that beta particles are electrons, the way they bend in these fields. He finally is able to bend alpha particles, not getting particularly good measurements on the electric mass charge, but certainly showing that they were heavier than the beta particles, and they had a positive charge. These the alpha particles had a positive charge as opposed to the beta being negative. You can see in the diagram, the beta particles are being bent towards the positive plate. It's being attracted to the positive plate. We know that unlike charges attract. So the beta particle is negative. The alpha particles don't bend as much. Why can't we bend those alpha particles as much as the beta? Because they're heavier. They're more difficult to knock off of their initial trajectory of going straight. So we know that they're heavier than the beta particles and they're attracted to the negative plate, and therefore they're positive. So these results, and finally gamma rays, we're not being able to deflect it at all. And this convinced Rutherford that these gamma rays are something different. They're neither positively charged or negatively charged, which would indicate perhaps that they're not a particle at all, but they truly are, perhaps the wave phenomenon being an electromagnetic wave. So a fundamental question was, where does this energy come from? We do have the notion of the conservation of energy. Energy just can't be created out of nothing. But it seems like the beta particles are being thrown out of the atom with a certain amount of kinetic energy. Alpha particles the same. Gamma rays altogether is even more energetic. Where is this energy coming from? It's not like the elements, that's the radioactive elements, are losing energy in any way that scientists can discern. It seems like this energy is literally coming from nowhere, which would be a tremendous violation of the conservation of energy. What really spotlighted this was when Pierre Curie in 1903 showed the great power, the great energy coming from radium. And that made radium and him and his wife an international sensation. This idea of this element, radium, having such power, discovered a new element, just captured the imagination of the popular press and worldwide. Just to show you the kind of thinking of a classical physicist, the ultimate classical physicist of the day was Lord Kelvin, the godfather of classical physics at the time. And just to show his thinking of how to explain this energy seemed to be coming from nowhere. No, it can't come from nowhere. So it seems to me, therefore, absolutely certain, he's absolutely certain, it seems to him, that if the emissions of heat can go on month after month, energy must be supplied from without. The idea of the energy being supplied somehow or other internally in the atom itself from nowhere was just not a concept of classical physics. So it had to be supplied from without, according to Lord Kelvin. I venture to suggest that somehow ethereal waves may supply the energy to radium. Somehow or other, these waves were getting into the atom, which then would come out as the radioactive energy. So this is the kind of thinking that we have during this period. This is the kind of thinking that's going to have to be overturned, and as we'll see, in a very radical way. And the key to this whole new discovery is the discovery of emanations, gases being given off by these radioactive elements. As far back as 1899, the Curies discovered that uranium was given off a gas. Indeed, a radioactive gas. They could capture this gas, separate the gas in a container from the element itself, siphon the gas off, and it itself was radioactive. It itself was giving off uranic rays of some sort. In that same year, Rutherford discovered that thorium, which was known to be radioactive, was also giving off a gas, a radioactive gas. And it turns out that these gases, these radioactive gases, was the way that researchers could delve that much further into the nature of radioactivity and what was going on. So let us see how that goes. We're here still in McGill University in 1900, and again, just a typical Rutherford story. We'll see this again in the presentation. It's happened more than once, even without me pointing out in the presentation. He's at McGill. He's the chairman of the Department of Physics. He pretty much controls his domain. Has a wonderful research facility, as one of the videos that I suggest you watch points out. And this young guy is hired, Frederick Soddy. He's hired as an assistant in the chemistry lab. He's not exactly a test tube washer, but he's not a research scientist in any way. He's there to help the lab experiments, set up the labs for the students, maintain the equipment of the lab, etc. Rutherford likes this kid, sees he's got talent. He says, come on, work with me. Work with me on my experiments on radioactivity. Forget about washing the test tubes. And Soddy becomes his research partner, and of course goes on, to win the Nobel Prize for the tremendous work that I'm about to describe. This is Rutherford, the teacher. This is Rutherford, the mentor. There's probably no one in the history of physics that can compare to Rutherford in this way. No one. Maybe the second one that I can think of that's kind of close is J.J. Thomson, because one of J.J. Thomson's great students was Rutherford. But when you look at the list of PhD students, research students, and young collaborators who worked with a scientist to go on to great things, there is no list that can compare to the list that you can comprise with Rutherford. It starts here with Frederick Soddy. They decided to study the emanation, which was a brilliant, lucky choice on their part, to study the radioactivity of the element and giving off this radioactive gas and trying to understand what was going on. And what they found from the gas, because luckily the radioactivity of the gas, we would say now, has a much shorter half-life. The radioactivity of the gas was diminishing very, very quickly, quickly enough that they could actually measure it. It's much easier to handle a gas, right? We have many chemical techniques of handling gas in all kinds of ways. Soddy, of course, was a trained chemist. So he could handle the gas, the amount of gas, filtering it in different kinds of ways, isolating it in different kinds of ways. And what they discovered was that the radioactive strength of this radioactive gas being given off by the thorium, the radioactivity of the gas was directly proportional to the amount of gas. Well, that sounds trivial, but the one more sentence is, and the gas was disappearing. The radioactive gas was disappearing before their eyes in their closed containers. And as the gas disappeared, of course, the radioactivity of the gas disappeared. And Soddy could measure that. And what he found was the amount of radioactivity of the gas was decreasing exactly in proportion as the gas was disappearing. This gave him and Rutherford the idea that the radioactivity was decreasing in some kind of a mathematical way. In this way, this directly proportional. And there's an equation that explains this, which won't mean anything to us. But the upshot is that if it's going away, disintegrating in proportion to the amount that's left, then we have the idea of a half-life. There's a certain amount of time where only half of the element exists anymore. Half is gone. And if it's truly proportional, if the disintegration is truly proportional to the amount that's left, in the next variation, the next duration, of that half-life, half will be gone again. And in one more iteration of that same half-life, whatever it is, half will be gone again. That's the mathematical consequence of the fact that the disintegration is happening directly proportional to the amount of radioactive element that you have. Gives rise to the idea of the half-life. And a graph would look like this. Here's a modern graph of cobalt-60, a radioactive element. And you can see that the half-life here is 5.27 years, not important. But here's one half-life, two half-lives, three half-lives. And you can see if you start with 10 grams, after one half-life, you'll be down to 5 grams. And then after another half-life, a quarter, two and a half, and then 1 1/4. You keep cutting it a half and a half. This is what they were able to discover experimentally. So one of the first things that this team of Rutherford and Soddy discovered is the phenomenon of radioactive half-life. The radioactive decay is happening in a very mathematical, predictable way. Why this is happening, they don't know. No one knows. But they're the ones who discover this phenomenon, the very, very regular mathematical way of disintegration. Of course, the question immediately is what does it disintegrate into? First of all, we have this, and the original radioactive element, I believe they were working with thorium, creating this radioactive gas. Well, they could see that it was difficult. It was not easy to see that the thorium was going away. Much easier because the thorium half-life is very, very long. You're working with a solid, very difficult to work with solids, very difficult to work with tiny amounts of solids to measure it. Those things can be done with the gas. And that's why the half-life phenomenon was discovered in studying these radioactive gases. Before we finish the story of Rutherford and Soddy working together, one other thing that Rutherford did while he was in Manchester, and this is my favorite example of the tremendous simplicity of his experiments, the absolute genius of his experiments, the simple materials and concepts that he uses. He's finally after what are these alpha particles. He knows that they're positively charged. He knows that they're heavier than electrons, but what the heck are they? And this is his experiment, guys. What he sets up is he takes the element radium. He knows it's giving off this gas, right? The Curies discovered that, giving off what they called at the time radium emanation. It was a radioactive gas. And the half-life of the gas is 4 days. Very, 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 very fast, okay, compared to radium, which, you know, is measured in a totally different time scale in years. So it's like working with fruit flies, you know, in evolution. These things are turning over very, very quickly. The radiation is diminishing very, very quickly. And it's a gas. They can replenish the gas. Funny story, by the way, it took a long time for them to figure out. They were trying to measure the half-life of the gas, and they kept getting inconsistent results, crazy results. Finally, again, Rutherford realized, well, you were taking measurements sometimes when the lab door was open and sometimes when the lab door was closed. When the lab door was open, the breeze was coming in, it was disrupting your gas. This is how they discovered, in fact, that originally that it was a gas, by noticing that the door being open and closed was changing their measurements. So they figured out they were working with a gas, and they had to take greater precautions in siphoning off the gas without having the breeze of the room disturb what they were doing. But anyway, getting back to our experiment, he captures the gas in a glass tube. He's got a gas in this glass tube, right? He knows it's itself radioactive. It's itself giving off alpha particles. He tells the glass maker to make the thinnest possible glass you can make, so that he knows that the alpha particles can get through this very, very thin glass. So he's trapped the radioactive gas, calling radium emanation, that was its name at the time, didn't know what the element was, captured it in this very, very thin glass tube, which he knew that the alpha particles were strong enough to get through. He takes that glass and puts it inside the vacuum tube, the Crookes tube, the cathode ray tube, which anytime he wants, he can turn on the juice and create electrons, right? That's what cathode ray tubes do. They create electrons. They create beta particles. So he lets the tube sit there for a couple of days. He lets the radio emanation do its thing, giving off alpha particles. He knows that the alpha particles, some of them are finding their way into the Crookes tube. He knows that they're positively charged. He knows that when he turns on the Crookes tube and releases these electrons, the electrons will be captured by whatever this positive charged alpha particle is. And with any luck, the alpha particle by the electrons will be turned into an element that he can recognize. That the alpha particles, that the beta particles, the cathode rays, the electrons, will neutralize the positively charged alpha particles into an element that he can recognize by taking the spectroscope. And that's exactly what he does. He takes a spectroscopic sample of whatever has been accumulating inside the Crookes tube, and sure enough, he finds the strong yellow line, unmistakable line where it has to be, of helium. And he knows that helium is the second element. Helium has a positive charge of 2. That's his alpha particle. he realizes that alpha particles are helium without the electrons, just the positive charge of the electron. He'll go further in a few years to go inside that helium and understand the notion of protons and neutrons. We're not there yet. All he knows is that the alpha particles is a positively charged particle with, which is the same as the helium atom, a mass of 4, a charge, a positive charge of 2. But you step back and look at the design of this experiment, the simplicity of it, the glass, the thin glass that allows out the alpha particles, knowing what he wants to do, letting them accumulate, and turning them on inside a pure source of electrons. He knows there's nothing going inside that tube from the outside. The only thing that's inside that tube, besides the electrons that are being turned on, is the stuff that came from the emanation. The only thing that went through that glass was the alpha particles. So when he identifies the helium, he knows that what that must be is the transformed alpha particles. That was the year, by the way, that he won the Nobel Prize in Chemistry for his investigations into the disintegration of the elements in the chemistry of radioactive substances. He, of course, was a physicist. He was a little chagrined that he won the prize in chemistry. He made the very, very funny remark that I've been studying transformations, for a very, very long time, but I never saw as quick a transformation as transferring a physicist into a chemist. We now turn to the work of Soddy. Soddy was very interested in this progression, what was going on. Thorium was giving off thorium emanation, a gas. Okay. What else was going on? What was happening to the thorium emanation? Was that the first change from the thorium to the thorium emanation, or was that the first one that he could detect? So he began a very serious study of this. And one of the things that was discovered was there was something in between. Didn't know what it was. He knew it was chemically different from thorium, chemically different from the thorium emanation gas, so he called it thorium X, another element. He continued this and continued this as the brilliant chemist that he was, breaking down, seeing what the radioactive element that he could isolate, what it turned into with this half-life phenomenon, and what that then trying to isolate that chemically, and then seeing if that broke down itself in a radioactive way to yet another element. Did these radioactive elements transform into other radioactive elements, which, since they were radioactive, would transform into another? You get the idea. And he finally searched this thing through until it would end inevitably with the element that he could recognize, lead, which was not radioactive, gave off no radioactive rays at all, alpha, beta, gamma. But he could isolate how many different elements there were between the original radium that he started with and the lead that finally ended up. Well, he found there were more different radioactive elements between the thorium and the lead than there were elements in the periodic table between thorium and lead. Yeah, even though there were some holes, okay, and the Mendeleev holes were even better understood during this time in the early 1900s and back in the 1870s. These holes were very much anticipated. So he knew how many elements there should be between thorium and lead, and he had more radioactive elements on his hands than he could account for. Well, the only thing that could be is this chain must be somehow or other reproducing some of these elements again, because they couldn't be all different. Periodic table didn't have that many elements to hold. So some of these disintegrations into other radioactive elements had to be repeating elements in the chain. But they had different weights that he could measure. He could measure the atomic weights of all these different radioactive elements, they had different weights, but yet they must be in some way the same element. And this, of course, leads to the idea of his greatest discovery, the idea of an isotope of an element. So here he begins to drill down, understanding. Here I have the half-lives underneath. I have the radioactive decay up on top. The thorium would give off an alpha particle, become a radium, which had a half-life of 5.7 years. The radium would disintegrate into actinium. Remember, that was the element discovered by Dubonnet, the researcher working with the Curies. The actinium had a very short half-life of only 6 hours. It would give off a beta particle. It would turn into something they called radiothorium. Didn't know what that was. Different element, different half-life of 1.9 years. It would in turn give off an alpha particle, giving off the good old thorium X, and the thorium X, which had a half-life of just 3.6 days, would give off finally the thorium emanation, which they started with. And this had a half-life of 1 minute. That was those fruit flies that he could work with, a gas which had a very, very high turnover. So he broke this up. As the brilliant chemist that he was, breaking up these elements. Yes, some of them, he knew there were different elements in some way, gave them names, but he discovered their half-life, their weights, what radioactive elements were being given off. This is just incredible, brilliant kind of work that only a Sadi could do. One of the elements, by the way, that was discovered, this radiothorium, he had an assist from a young chemist working with William Ramsay. Sadi eventually goes to work with Ramsay. Remember, Ramsay's the one who discovered all the noble gases back in 1898, the neon, the argon, etc. So any chemist wanted to work with the great William Ramsay. And he took on a young German chemist at the time, Otto Hahn, who in his study in Ramsay's lab discovered a new element in this chain of the radiothorium. We will meet Otto Hahn again. So I wanted to bring him up. And it's amazing how these great scientists work for all the other older great scientists. It doesn't seem to be a coincidence that if you want to be a great scientist, it really, really helps if you are mentored, if you are trained by another great scientist. What Sadi discovers is what he calls the displacement law. And we'll see what he means by the displacement. What is the displacement of what? These elements are moving, they're being moved, they're being displaced in the periodic table. This is how he envisions it. So here's the picture I just showed you, but let's trace it in a different way, the way Sadi analyzed it. We have the thorium, has an atomic weight of 232. He knows that that's radioactive and gives off radium with an alpha particle. Okay, he knows that the alpha particle has a weight of 4, so thorium loses a weight of 4, goes from 232 to 228, okay, 4 less, gives off an alpha particle. He knows that the radium then gives off a beta particle and becomes actinium. Weight doesn't change because a beta particle is an electron, virtually has no weight at all. So the weight doesn't change, but the element changes. It now becomes actinium. Another beta particle is given off. Weight still doesn't change. It's still at 238, but it gives off this element radiothorium, discovered by Hahn. And then finally, well, which then he discovers finally that it has the same chemical properties as thorium itself. So radiothorium was well named. It has the same chemical properties as thorium. But notice it's keeping this weight of 228. And then finally, getting down to the thorium X, his discovery, an alpha particle will bring you down to thorium X, which again, now we lose weight of 4 from 228 to 224. So he looks at this thing. It goes from thorium to radium to actinium to radiothorium. He has alpha, beta, beta. And alpha, beta, beta brings you back to thorium. Start down with the radium at the 228. Beta, beta, alpha brings you back to this thorium X. If the thorium brought you down to radium, then this thorium here, the radiothorium, should bring you down to radium. This also, this thorium X, should be radium. Starting from thorium, if alpha decay gives you radium, starting from thorium, even though it's a different weight, alpha decay should bring you back to radium. This is his hypothesis. This is what he goes after as the chemist, and is able to, in fact, prove this. This is the displacement law, because what he finds is an alpha, beta, beta brings you back to the same place in the periodic table. The thorium will come back to thorium. The radium will come back to radium. And in fact, he even, by confirming that the thorium X is in fact another version of radium with a mass 4 less than the radium that's over here. But they have exactly the same chemical properties. So he states the law as follows: the successive expulsion of 1 alpha and 2 beta particles in 3 radioactive changes in any order brings the interatomic charge of the element back to its original value. The positive charge of the element, the interactive atomic charge, comes back to the original after a alpha beta beta, or beta beta alpha, or even beta alpha beta. Doesn't matter what order you find the radioactive disintegration going on. And the element back to its original place in the periodic table, although the atomic mass is reduced by 4. And this is where he gets the word isotope. Isotope means same place. And so now when he looks at this decay chain that he's been studying so intently, it's the same chain. I've now just simply put the atoms up on top. You go from thorium 90, radium 88, actinium 89, same weight, back to thorium, but with a much lower weight, from 232 to 228. The radium 228 winds up as radium 224, okay, and finally down to the new element discovered, radon. That's the emanation. That's the gas. Okay. So this is the great early work that Sadi does, in which he wins ultimately the Nobel Prize. I'll stop here. Just give me a few more to come to a natural place to stop this particular story. Why was radioactivity so difficult to figure out? This took a long time with many, many scientists. Rutherford, Hahn, Ramsey, Sadi, these are the great names, but many, many scientists working on this, as you can imagine. Radioactivity is one of the most fascinating phenomenon of the time. So many people wanted to work on it. Why was this so difficult? Well, here's an answer here. Here's the radioactive decay chain of uranium. And although it starts simple, here's the original Becquerel uranic rays. This was uranium turning into thorium. Here is the pitch blende discovery of radium itself, the Curies. And here's that original radioactive gas coming from the uranium. This is the radon. But once we get past this, look how complicated it gets. Yeah, we wind up finally with lead, unradioactive, neutral, stable lead. But boy, to get there, we go through 2 other leads, 2 other radioactive leads in this very complex chain. Once we come down here to polonium, right, another element discovered by the Curies, it can go in 2 different ways. It can give off a beta particle and become acetane, or it could give off an alpha particle and become lead. But we're not finished with this lead. This lead moves on to other things, another plutonium. You can see how complicated this is. The difficulty that chemists had of separating, because this bismuth, these 2 bismuths are exactly the same chemically. There's no chemical way to separate these. There's no chemical way to separate these 3 leads, but yet they're different. They have different weights. They have different radioactive elements coming out. They have different here. Even elementary, even radioactive rays coming out sometimes. So this is the simple answer to why this took so long, so many blind alleys to finally work out the mechanism of radioactivity. Started in his speech, the layman's speech that you give when you win the Nobel Prize. They're wonderful speeches to read because you learn so much about the current research at that time from the people doing it. And here's just a remarkable statement that I pulled out of his speech, given now in 1921, reflecting back on the work that he and Rutherford did, discovering the half-life process, and then discovering these what's called the radioactive disintegration, the transmutation of elements from one to the other. These are these chains of transmutation. The interpretation of radioactivity, which was published in 1903 by Rutherford and myself, ascribed the phenomenon to spontaneous disintegration of the atoms of the radio elements, whereby a part of the original atom was violently ejected as a radiant particle, and the remainder formed a totally new kind of atom with a distinct chemical and physical character. These disintegrations proceed successively, a large number of times. So these result in a series of more or less unstable new elements. Between the original parent element and the ultimate unknown final product, there was a theory sufficiently challenging to the accepted doctrines of chemistry, a classic British understatement. The theory was sufficiently challenging to the accepted doctrines of chemistry. This was a complete sea change of what chemistry was since the days of Dalton and Lavoisier, that a chemical element left all by itself could simply change into another one. And it wouldn't stop there. That guy would change again to something else. This was something totally unanticipated. When radioactivity was discovered by Becquerel, a notion like this was totally out of the question. But yet this is ultimately what Becquerel discovered, this process. One will look at the decay chain. This is the decay chain of thorium, going into radium, then to the actinium, back to thorium. And here's the three-step rule: alpha, beta, beta, right? Going back to thorium. Here's another one, going from polonium to polonium. Polonium, alpha, beta, beta, brings you back to the same place in the periodic table, coming back to the same element but with a different weight. We go from 216, we fall to 212 because of the loss, basically, of the alpha particle, of the helium nucleus. Okay, Greg, do we have any questions?
Yes, we do, Peter. Andrew Sherman has a couple questions. What was meant by energy from radium? How was its power made apparent?
Just literally by the penetrating power of these rays. Once they understood they were dealing with alpha rays and beta rays, understanding what they were, these had tremendous energy to go through materials, to find their way onto a photographic plate, lighting up a phosphorus screen, disintegrating, just discharging an electroscope. These rays could do things, and you could measure the amount of energy by how far they could go through physical objects, how quickly they could neutralize electroscopes, become all kinds of ways of measuring the energy of these things. One of the early units of the measurement was the Curie, ultimately named after Marie Curie. So there are many ways of measuring the energy. Ultimately, with the beta particles, measuring their charge to mass ratio, putting them into Thomson's tube, you could actually measure their speed. You could actually measure their kinetic energy, 1/2 mass times velocity squared. So they became more and more adept at quantifying the energy coming out of these radioactive atoms.
And the second question from Andrew. So did the alpha particles become helium in the Crookes tube?
That's exactly what happened when Rutherford released the electrons. The electrons were attracted to the positive helium nuclei. They were captured by the helium nuclei and became helium atoms. He was able to identify them by then exciting what was in the tube, the gas that was in the tube, and sure enough, there was the spectral lines of good old helium gas.
And one question from Pamela and Blair. How come those emanated elements from thorium didn't appear in the periodic table like actinium?
They eventually did, and it's funny that you asked that question because I'm just about to show the sequence of some of the elements that were discovered. So, in fact, they were discovered. Once they were understood and they were chemically different and they had different weights and they were moving into different elements, the immediate question was, well, what are these different elements? Okay, and so allow me to proceed because I would like to answer exactly that wonderful question. Thank you, thank you for the lead-in. So here we have the periodic table of 1898. The latest thing that was put here was the noble gases here, done by Ramsey and his team. And let's just go through what radioactivity was. By the way, there were 13 holes here. Not all anticipated. Certainly the ones up here are all anticipated. Maybe not originally, not all of them originally by Mendeleev. Some of them were, certainly this guy, very, very early on, right? He's so high up. It's interesting why he hasn't been discovered yet, right? These guys down here can be troublesome. They have chemical properties very similar. Wasn't clear how many of these there were. But let's just go through. I think this is a little fun. So we start with polonium here, discovered by the Curies in 1898. And then soon after, we get radium, same year. Okay, this is the great sensation of the Curies. And then we come to actinium, the very next year by a member of their staff, Dubonnet. Okay? So we've got three. The next one here is europium. Not a very interesting story of how this was discovered. Was not discovered, I believe, with the phenomenon of radioactivity. This was a pure job of just brilliant chemistry. We go to this guy here, LU. What is LU? Let me see. I think I wrote this down. Luteum, element number 71. Luteum is an interesting story. It was discovered by three chemists independently in three different parts of the world in 1907. One of those chemists was working for, his name was Charles James. He was working for the New Hampshire College of Agriculture and Mechanical Arts of 1907, that eventually became the University of New Hampshire. Okay? So he is one of the great members of the faculty of the University of New Hampshire. I think there's a plaque to him up there at the university. He was a great chemist. Not only did he discover element number 71, but he discovered a whole new way of isolating elements in this kind of a row. This row here was very troublesome. They all were very, very similar. He discovered a number of different ways of precipitation and crystallization of these elements out of different mixtures to isolate them in different ways. So this is Charles James, and I believe there is a plaque for him up at the university. So that's number 71. We're not quite finished. We're almost there. Radon, can't forget that radon was discovered late. This was the great emanation. This was the original gas emanation. Finally, this was isolated by Ramsey and his team in the early 1900s. And I think we may be done. Was there one more? Oh, yes, of course. Proactium, okay, element number 91. You can see the ones that I've checked off, they're all, most of them were involving radioactivity. So radioactivity had a great influence on, by here we are in 1913, what the periodic table looks like. a lot of elements being filled in. When you look at this thing, in 1913, I think two things kind of strike out as a little curious. One is that here's the most famous two families, right? This is the sodium chloride family, where all the salts are being made. And it's interesting that the last two elements were not yet discovered. They certainly were anticipated, right? They're completely surrounded. This element here is surrounded by radon and radium, right? He's surrounded by polonium and radon. These guys were anticipated, but yet still in 1913, they're both not discovered. Must be an interesting story to them. And there is, and I'll tell that when we get to it. But I think this is the most intriguing of all. This guy is very high up, element number 43. There's no one near him. Everything has been discovered, until we get to what, 56. He's 43, and yet he remains unknown. This hole has been here since Mendeleev, okay? This is a well-known hole in the periodic table, and yet here we are in 1913, and it's still elusive. The chemists, tremendous amount of time and effort has gone into trying to find this guy, and still, at least in 1913, and we'll find for 20 more years, this guy will not be found. So this must be an interesting story, what element 43 is, and it is, and I'll enjoy telling you that when we get to it in our chronological story. Okay. You asked me, it was so intriguing how we measure atomic masses, atomic weights back in the old days. Well, let me show you how it's done now in the new days. And this is the apparatus, the mass spectrometer that was invented by another student of J.J. Thomson, Francis Aston. Thomson was working with the student Aston, and they were curious about the gas neon. Neon, they knew, had an atomic weight of 20. They could measure that the old-fashioned way as a gas. Gases were easier to manipulate. But when they measured the gas accurately, they found that it wasn't 20, it was 20 point something. And they didn't quite understand why that was the case. Aston had a brilliant idea of taking Thomson's design of the cathode ray tube, and instead of just, bending it in a way to control, where it is and what its mass to charge ratio is, and letting it sweep across the screen, for a television picture tube eventually. He said, why don't we just let's just, we have our cathode ray tube. We know that the beta particles, the electrons, go in one direction, and if it's a gas, as with the hydrogen gas, with the neon gas, we know that they will be ionized and they'll go the other way, going towards the cathode rays. So let's take the neon gas, which has now been ionized, and let's accelerate it towards the negative cathode because it's positive, right? It's lost its electrons. So let's accelerate it through the cathode and let's send it through a strong magnetic field. If they, in fact, are different weights in that gas, the lighter elements will be bent easier than the heavier elements. So let's send it through a uniform magnetic field and just break it up by mass. And so the phrase, a mass spectrometer, just as a prism is a light spectrometer, creates the spectrum of different colors, we have the idea of the magnetic field. This device will break up the spectrum of the masses of the different ionized gas atoms. And that's what they did. This is the prototype of the mass spectrometer, and they had great success. What they found was this. When they collected the masses at two different places on their electric plate, by having two different directories, one being bent more than the other, they found a lot of ions of weight 20. Okay, bent more than the heavier ones. But they did find a significant amount of ions collected which would have, according to their trajectory, according to their equations, basically worked out by Thomson, of knowing where a different weight would fall on their plate by what kind of trajectory they would have, how the magnetic field was bending it, and with all the different dimensions that they could measure, they did in fact have a measurable amount of a weight of 22. But this was pure neon gas. That they knew. I'm sorry. Yeah, that's right. Pure neon gas. They could not chemically separate these two elements. They were neon gas. There was no impurities inside that tube. But yet they had two different weights of neon gas. And here's the kicker, guys. Neon is not radioactive. There are, in fact, in nature, two different isotopes of neon without it being radioactive. There are two stable and always stable and non-disintegrating versions of neon. This was a very big deal. This was a big, big discovery. And that you could even have isotopes of non-radioactive elements. What the heck is going on? What is creating these isotopes? What is making two atoms of neon with exactly the same chemical properties, with the same positive charge of 20? Why did they have different weights? What was different? They had no idea. Something was making the element, the neon of weight 22, two masses heavier, two hydrogen atoms heavier, because that's the unit of the smallest mass of atoms, than the abundant version of neon of mass 20. But they had no idea why. One thing that they did know, it didn't change the chemical properties of neon. It didn't change it one bit. The only way to separate it was with this device of the mass spectrometer. And by the way, say this is the way we can take very, very accurate measurements of atomic masses now today, using much more sophisticated versions of this initial device of Aston, who won the Chemistry Nobel Prize for this thing. In fact, by 1922, using his mass spectrograph, he was able to identify 220 naturally occurring isotopes. So this was an incredible device to be able to do this. Turned out to be very easy in that sense of separating different isotope versions using his mass spectroscope. Okay, let me quickly just mention the radioactive dating, because I think this is fun. You know, I did want to show different kinds of applications of the stuff that we've been going through with our course. Radioactive dating certainly is one that we all know about. Here's our chart again of the half-life. Once this is understood for an element, here's the idea. The idea is, suppose that you knew for in a certain definite event of the life of an element, sometime in its past, just how much of the radioactive substance there was at that moment. You had to know what it was back in the past. Of course, you have it now. You can measure how much is there now. You can measure how much is left. If you know the half-life, you can figure out how many half-lives it takes to get down from what you knew you started with, which is the trick, I understand. You have to know how much you started with way back when. But if you could know that, if you knew how much of this radioactive element there was at the beginning of this particular event that you could identify, you can certainly measure how much radioactive of the element is left. You could count, in a way, I put in quotes, mathematically, you've got to use some equations, but you could count how many half-lives it takes to get from where it started to where it is now. That's the basic idea of radioactive dating, okay? So let me give you an example. Okay, let's do some simple arithmetic. Suppose that you have a sample of a compound, a mixture of stuff. In there are two elements, A and B. A is non-radioactive and stable, B is radioactive. Suppose you have 90 grams of the A and 10 grams of the radioactive B. You also know that the half-life of B is 1,000 years. Okay, so that's where we are right now with this 100 grams sample. 90 of the non-radioactive stable stuff, which has always been there, and only 10 grams left of the radioactive element. And here's the kicker. Suppose that you know, some way or other, by some magic, you know that when this thing first formed, when you find this compound, you always find that 60% of it is A and 40% of it is B. Suppose that you know this, okay? Because you study the current stuff that's just being formed, and you can see that it's always the same. We have an old sample, yes, but when you look at a new sample, it's always 60% A and 40% B. Well, that's all you need to know, right? Because if you know that the original weight was A plus B, now it's only down to 100. But if you know if the 90 grams weighs 60% of the original weight is 150 grams. If you know that 150 grams, 40% of it originally was B, that means we started with 60 grams of radioactive B back in that event that you can identify. So we have 60 grams at the beginning, we now have 10. Well, it took 1,000 years to get from 60 to 30. It takes another 1,000 years to get from 30 to 15. And let the mathematicians figure out it takes 660 years to get from 15 down to 10. And so we can date this thing as 2,600 years old. Okay? This is the fundamental idea of radioactive dating. With real numbers, right? Carbon dating, we use radioactive carbon, carbon-14. It disintegrates into nitrogen-14 by giving off a beta particle, the electron. Notice the mass doesn't change, it stays at 14, but the actual electric charge goes up. It loses an electron. It loses a negative charge, and the positive charge goes up by 1. Has a half-life of 5,700 years. And what's the trigger that we know? When things are alive, guys, we know how much carbon it makes up a living tissue. What percentage of it is the stable carbon-12, and what percentage is the stable carbon-14? It's not exactly 60%, 40%, but it's a known ratio that the carbon-14 makes up a very definite, I think it's, 1%, 2% of our body right now, of the carbon in our body is made up of 99% carbon-12 and 1% carbon-14. And that carbon-14 continues to be regenerated and supplied into our living cells as long as we're alive. When we die, that process stops. So when you look at a fossil where the organic processes have stopped, the carbon-14 is beginning to disintegrate. And that's how we know when we go ahead and take the fossil sample, see how much is left, we backdate it up to how much carbon-14 there had to be in the beginning, and how long would that take to disintegrate to where we are now. Okay, the basic idea of dating things using carbon-14. If you use a different kind of element, not a half-life of 5,700 years, but maybe something like, oh, I don't know, maybe 4 billion years, you can begin to date the rocks in the mantle of the Earth to find out how old the Earth is by seeing how much radioactive material is in the ancient rocks of the Earth. Same basic idea, though. Okay, see if we can finish up quickly here, the end of our presentation. So we're done with the early discoveries of radioactivity for the moment. We turn our attention now to the work of the atom itself. By 1900, people agreed that atoms were made mostly of electrons. I know it's a little crazy, but people went electron crazy. And they thought atoms were just made up of thousands of electrons, somehow or other being neutralized in some way. There were other ideas besides the crazy electron theory. The planetary orbits was an idea, which will come back. The electrons were maybe orbiting in some way. There were ring structures. The electrons were in structures of rings, which we'll, of course, see in the modern theory of chemistry cells. These ideas were all thrown around. Our friend Philip Leonard, who never seemed to have gotten any of the final things right, he had an interesting idea. He had an idea that since the atom was neutral, that there were these electrons and these positive charged elements, and they always came together so that everything was neutral. And this is what accounts for the different weights of the atoms. Okay, this would here have a weight of like 4. They were neutral because the electrons and these positive things were paired up, and they could kind of float around inside the atom, making up the size of the atom. And the atom was mostly empty space, using his idea. Interesting kind of, set of ideas. Some of them have merit, some of them. Where did it come from, the idea that the atom was mostly space? Through his Leonard windows, because he could shoot those beta particles. He could shoot the electrons so easily through the thin foil that they weren't being stopped. So what was, the thin foil was mostly empty space, because the beta particles would get through so easily. The cathode rays would get through so easily. So we got some of these ideas right, but again, he didn't have the luck of. Thomson finally moves away from his thousands of electron theory and comes up with the very famous plum pudding model, the one before Rutherford's model. And here the idea is pretty simple. The idea is that the positive charge of the atom is just this big blob. And that's where all the weight is, because electrons don't weigh anything. So if you have, for example, carbon, which has a positive charge of 6 and 6 electrons, then the 6 electrons are kind of scattered through the positive blob like plums in a pudding or raisins in a cake, or the various different watermelon seeds in a watermelon. You will get different analogies of the Thomson model. And it was an interesting idea. It made the atom electrically neutral, which it has to be. It accounts for the weight of the atom, the different weights, because these positive charges would get, I don't know, bigger and bigger, heavier and heavier. And it accounted for where the electrons were. The electrons were inside the blob, and they could be thrown out by making them very, very hot, and they be thrown out of the cathode metal by being excited and finally thrown from the bonds of the positive blob and sent out as the original cathode rays. So I don't know. It had some merit, but it had some real serious weaknesses. And these weaknesses are very interesting because they're weaknesses of all the atoms until we really almost get to the Bohr atom. One is what makes these different atomic weights? That's the thing we raised just a moment ago. What's with these isotopes? Why are these blobs of neon different weights? They're not holding different electric charge. They're not holding a different amount of plums, different amount of electrons. Why do the blobs have different weights? Didn't seem to have any easy answer to that. It's certainly, these blobs certainly were not going to explain the periodicity of the periodic table, of why you would have, families of common chemical properties. These differentiated blobs weren't going to help you understand that. And finally, very, very importantly, what was the spectra of the individual elements? How would these blobs and these electrons just kind of floating around there, why would they lead to the different beautiful colors of the spectra of the different elements? The 4 colors of hydrogen, the 6 different colors of helium, et cetera, how would these undifferentiated blobs give rise to these very, very distinct, clearly somehow or other, I don't know, discrete individual colors coming out? A model like this was hopeless against questions like this. And these are the fundamental questions that people were trying to answer. So although this was a popular model for a while because it was the best that they had, Rutherford liked the model. Rutherford was a student of Thomson. He was going with it as best you could, until the great famous gold leaf experiment. Let's see if we can get through the gold leaf experiment, and we'll stop there and finish off the last few slides next week. Just a couple of minutes, but I don't want to rush this. But we do want to go through Rutherford's famous gold leaf experiment, coming to the discovery of the nucleus. Rutherford was sending alpha particles through the atoms, and according to Thomson's model, not surprisingly, just as with the Leonard window, they were going right through. The atoms seemed to be mostly empty space. The alpha particles were heavy enough to get through and not being knocked off course in any way. And that seemed to be some kind of confirmation of this idea of Leonard, the idea of Thomson, of the electrons really not creating any kind of barrier for the heavy alpha particles to get through. Okay. They even could measure the deflection angle, and they found there was really no deflections at all. The alpha particles really didn't spread out very much at all. It mostly went right through the gold foil. Until one day when it didn't. Story goes that one of his collaborators, Hans Geiger, Geiger counter fame, a great scientist of his own right, coming over from Germany to work with Rutherford. Anybody who was anybody wanted to come work with Rutherford. So Geiger was working with Rutherford and he was in charge of the gold leaf experiment for Rutherford. And Rutherford said, so how are things going? He says, well, it's just most of the alpha particles just go right through. He had the ability to have this, scintillator telescope, see if anybody was coming at different angles. He could swing it up this way, swing it back this way, but most of the business was right in the middle. You swing this thing up too far, and you could watch. You had to be in a darkened room, keep looking and looking while the alpha particles were being released, and seeing if you found any here. You could watch for hours and see nothing. You'd go bleary-eyed. If you watched here, you'd be bombarded by little points of light as they were coming in, lighting up the screen. So the story goes that Rutherford, of course, keeps track of all of his experiments. Asks Geiger how things are going. He says, well, it's just nothing's really not new. Most of the particles are coming through the center. So he says, you got this young kid working with you, don't you? Undergraduate, Ernest Marsden. Okay, look at his age. This is 1909. He's born in 1899. He's 20 years old. He's not even a graduate student. He's working with Geiger. And he says, well, there's an undergraduate. Rutherford says, he's an undergraduate. He has nothing better to do. Tell him to swing the telescope all the way around to the back. And just sit there for hours and hours and just see if anything comes up. Just see if something lights up all the way around, as if the alpha particles got knocked all the way back. Geiger says, well, okay. I'd be like, I don't see much over here. You want me to bring it over here? All right, we'll bring it over here. We'll look at it 180 degrees, 160 degrees. We'll let Marston do it. He's 20 years old. He has nothing better to do. And that's how it was discovered. In a very short order, Geiger comes running to Rutherford and said, we got reflections. We got alpha reflections being knocked back virtually straight back from the gold foil. And here's the picture of the alpha particle coming through, being knocked, virtually back almost 180 degrees here, being knocked back 150 degrees. And this was discovered by the young Marston, who, by the way, went on. Rutherford took good care of him, got his degree, got him a job back in New Zealand, back home in the University of New Zealand. I had a very, very nice career at the University of New Zealand. Rutherford set him up. And so here's where, let's stop here. I don't want to really go over with you guys. You guys have got to go. So we'll stop here, kind of analyzing what Marston found and the way that Rutherford was able to make the conclusion that you're looking at in an atom, a very, very heavy, very, very tiny nucleus. Okay, we'll stop there. Greg, any questions?
Yes, Peter, we have a question and some information. Jim Talbert asks, what are the, quote, chemical properties, end quote, that they observed to verify the similarity of the element and the isotope?
Well, there's all kinds of different chemical properties, that people have. One way, for example, is if you can vaporize this thing to take a spectrum of it. And when you look at the spectrum of the 20 mass neon and the spectrum of the 22 mass neon, they have exactly the same spectra. They have exactly the same colors that are in the emission spectrum. You can make elements with different compounds. They'll, for example, sodium will combine with chlorine and make salt. And again, you'll have different isotopes of sodium. It'll make exactly the same salt. There'll be no difference, and it's things like, and of course, much more sophisticated things than I'm giving. I'm not a chemist. But the various different chemical properties, not only the elements themselves, but of the compounds that they enter into and their chemical properties, how they precipitate, given certain temperatures and stuff, all kinds of things that you can imagine can show these, these similarities of the different weights of the isotopes of the elements.
Okay, Kenneth Eaton has a statement. Just a heads up, there is a free book on Audible called Quantum, really interesting. And if it is the book Quantum by Manjit Kumar, which I've read, it is a very good book.
Oh yes, I've read that book. That is an excellent book. Thank you for mentioning that. Who mentioned that?
Kenneth Eaton.
Kenneth, thank you very much. That, I agree with you. That is a wonderful book. If you're looking for a history of this whole thing that I'm going through here in bare bones and the theory, I can't recommend the book more highly. Before we get to that, I did want to show you, this is a live link here. This is a very nice film. I didn't give it in the Wednesday email because it's here. Take a look at this. This is a nice video of the gold leaf experiment and its results. About 6 minutes long, very, very well done. Okay, let's open up.
Sorry. Yeah, one more question in the chat room.
Yes, sorry.
Mary Covington asks, two practical questions about the lecture. When will this lecture be in the YouTube series of lectures, and how do we access it? Is this explained in one of our emails?
Okay, Mary, you have been paying attention, but that's okay. I still love you. I'm kidding, Mary. First of all, I get the lecture out usually by this afternoon. If you look at any one of your 3 Wednesday emails, you'll see that I've given you a link to my YouTube channel. You might not realize what I'm saying. What I'm saying is if you press on that link, up will come, your website, up will come, your browser, and up will come my YouTube channel, which has all of my YouTube videos going back to, when we started this Zoom stuff with the pandemic. The very last ones up at the top, you'll see, they're all clearly marked. It'll say lecture 3 in quantum, lecture 2, lecture 1. So lecture 3 will be out by this afternoon. So just click on that link, go to any one of the 3 Wednesday emails, find that link, my YouTube channel, and you'll see all of the lectures.
Thank you.
Okay, can we open up the mic? Anybody who's still around? Any other questions people want to throw out or comments?
Thank you. This is absolutely fascinating. It seems to be a key, well, I don't know, maybe the key lecture. Am I right?
This certainly is a key lecture. We have one more really coming up when we do the quantum atom, the quantum itself.
Sure.
And once then we can go to town. Then we can go to the Bohr atom and then finally go into quantum mechanics. But in a sense, almost all of them are key. We're building up a story here. So, all right, everybody, have a good week. This has been great. We will finish off very quickly the last idea here. Very important, couple of important ideas we haven't gotten to, and then we'll start the quantum atom. Okay, guys, see you next week.
Thank you very much.